Welcome to the next session of Strength of Materials. In this session, we will start with a new topic of columns and struts. First, we'll discuss about what is a column. A column is a vertical structural member carrying an actual compressive load. A column is something which is very much prevalent and everyone is aware of it. Sitting at a home or in an office, you can look around and you can see that column is a vertical member which is always axially loaded, which means the load is applied along the axis of this member. So hence it is called as axial load, and compressive because the load which comes on the column is always of compressive type. It is actually a load carrying member of the structure. It is the main member of the structure because if you know, the columns are the first thing that are built. When you are making a building, you will first make the columns, then you will go for making of the beams. Then you will work on the floors and finally the walls are made. So this is the main member of any structure. It is usually long as compared to its cross section. Now when I talk about a column, say if it is of a rectangular cross section, then this length which you see of the column L will be quite greater as compared to its breadth and its width. There is a possibility of buckling of this column. So that's the reason why we are studying over here. We want to study about these columns which get buckled or bent when a load is applied on it. Buckling is also called as vertical bending of a member. Now next we'll talk about what is a strut. A strut is a structural member carrying an actual compressive load. It is similar to a column except that it is usually short in length. It is a component member of a truss or a mechanism. Now for that you can see these figures. Here you can see that this is a truss and this is a strut which is carrying the load. For a mechanism like in the suspension system, you can see that there is a strut over here, and same way this is a strut which is carrying the other members. Strut, if you check in a dictionary, you would know that it is a member which carries or which is subjected to pressure in the vertical direction. So here if you see, there will be pressure from the upper end which is exerted on this strut, and it is supposed to resist that. There is no possibility of buckling of struts. Struts being very short in height, when you apply the load, it can break due to crushing, but it will never buckle because it's not long. Anything that is very long can show this kind of a bending effect, but not something which is short. Load carried by the strut is small as compared to that by a column. It may be horizontal, inclined, or even vertical. These are the three types of struts that are possible. Next we'll talk about crushing load. The load at which member fails by crushing only is called as crushing load. So suppose if I talk about this strut, here you can see that when a load is applied P on it, this member is showing a crushing effect. So this is called as crushing load P. You may also call this as PC, crushing load. P is load, C is for crushing. Next we'll go to the topic of crippling or buckling load. The load at which the member just buckles is called as buckling or crippling or critical load. Now as we have just discussed, this is say a column. Say for a building there are 4 columns of this sort. These columns will then be connected by a beam, and then you will have your flooring over here and the walls come in this zone. Now if you look very carefully, this beam is supported by the column. So when you study in the chapter of deflection of beams, we say that there is a beam and there are some reactions from below. So this is that beam here, and these are the columns which are providing the support, and on this beam is going to be another set of columns which are resting over here. So again there will be more columns and more beams, and that is how your building is going to be formed. So these beams will now be subjected to support reactions, and because there will be wall and something attached say on the wall, so they will be applying the load on this beam. So that's how this beam is going to be subjected to load. Now when load is applied, this beam may show some amount of deflection if it is not properly designed. And when these beams are loaded, they are going to in turn apply load on the column. Because of excess load, these columns may tend to buckle or bend like this. The way the beam is bending in this fashion, your columns may buckle in this fashion if they are too long. So this kind of a buckling or crippling, the load which is applied for causing the buckling or crippling is called as a buckling or crippling or a critical load. Now for that, in these days you can see that the columns are made not only of concrete but there are steel structures inside. This is a composite material, actually you can call it. These steel rods are called as fibers, and the concrete, gravel and the mixture that you have or you pour inside is going to be called as matrix. So this is a composite structure. Now the role of fiber over here or the rods is to bear the load, and the matrix is poured inside to keep the fibers in place. So this is all about the columns and the beams and the buckling or crippling that can happen in the columns. Now for that, this kind of a structure is made so that the buckling or crippling doesn't happen. But if at all it is to happen, it would be something like this. This is called as buckling failure. And when you apply the load on a short column, what you can see is a crushing failure. Next, we'll talk about types of columns. Now, these columns, as I have shown you in the buildings that are present, these columns can be of mainly two types. One is called as long column and the other is called as short column. Now, when we say about a column, say if it is of rectangular cross section, this is length L, width B and depth D. These are the three dimensions. The ratio of effective length to the least lateral dimension is greater than or equal to 12. Then this ratio, if it is greater than or equal to 12, we say that it is a long column. Now effective length means this is the entire length of the column. But out of this length, it is possible that some amount of length is not considered or is not affected by the load which is applied on it. We will discuss that in some time, what is effective length, but as of now you can just take it as an effective length or the length over which your load is being applied or the length on which the load is going to show effect is effective length. And least lateral dimension means these are the two lateral dimensions, if you can recollect. This is a longitudinal dimension, these two are lateral dimension. So in these two also, since it is a rectangular cross section, as I said, either B or D, one of the two will be lesser in value. So the least one is taken into consideration while taking up the term least lateral dimension. So let me say that this depth is less than the breadth. Then here the ratio will be effective length to the depth. And this ratio, if it is greater than equal to 12, then we'll say it is a long column. And such kind of columns will fail due to buckling only. The next type is short column. When this ratio is less than 12, it will fail either in buckling or in crushing, either of the two. This is called as short column. Now in between these two columns, there is another type which is called as medium column. Now you must be wondering that I have taken up all the values greater than equal to and less than 12 over here, then which value actually remains? But this is a concept of theory, pure theoretical concept. When you talk about a practical application, then this L by D ratio is quite greater as compared to 12. For example, it can be say 13.5, it can be 15 or 14.5, something of that sort. And when I say a short column, this ratio will be something like 6, 7, 8, 9. So you can see here that there is a range of values which are not covered at all. So these values will fall under medium column. So in medium column, obviously there is an effect of crushing and buckling. Now if you understand very clearly, buckling is a bending effect and crushing is something which is a direct effect. Direct means when you are applying a load P, the stress will be directly P by A. Instead of causing this kind of a crushing or compressive effect, it is causing something which is called as buckling, that is bending. And we already know that bending is because of an indirect stress. It is an indirect phenomena which happens on the body. So in medium columns, what you see is a combination of crushing and also a little bit of buckling which comes into picture. But in general, if you observe in practical applications, what is a medium column? Neither a long nor a short column. Now this will come with experience of the person who is designing. You must be wondering that if in theory it is not there, then how come in practical we are doing it? It's because everything in theory need not be converted into practical. There will be certain things which are practically possible. For example, I could say that the flow of water through a pipe should be 5 liters per second according to theory. But when I come to practicality, it will be around 4.8 liters per second. So where did this 0.2 liters go? It has gone in losses. When you talk about theory, there you are going to talk about completely systems which are perfect. But in nature, things are not completely perfect. They are all imperfectly perfect. So that is where your error comes into picture, or you can say some kind of a loss comes into picture. So here there is no loss as such, but yes, there is definitely something which is practically possible. Okay, we'll now go to the next topic, that is Euler's theory for such kind of a long columns. Euler has given his theory for calculating this critical or buckling load for long columns only. Euler derived a formula for the stability of long columns. In Euler's theory, the column fails due to buckling only. So this is something that we need to take note of, that in Euler's theory, we are not going to talk about short columns. We are only talking about long columns, and they are going to fail only under buckling. The effect of compressive load is neglected. Now this is very obvious because we are not talking about short columns. So we don't have to talk about the direct effect of that load. We will be only talking about an indirect stress or indirect effect on the body, that is bending. The effect of direct stress is neglected because the direct stress induced in long column is negligible. That's what we are considering as compared to the bending stress. So when you talk about long columns, they generally tend to buckle very easily. Now you can do this with your notebook. Suppose if you hold your notebook in this fashion, this is your notebook, holding with your palms, when you apply load from both the ends, you will see that your notebook will bend if it's a long notebook. If you have a very strong, sturdy notebook, this will not bend. This will directly show some kind of failure, but this will not bend. So a long notebook, if you hold in your hand, or it's a piece of paper that you're holding and you apply load, you will see this kind of a bending in your book. This theory is not used for short column because the direct stress is considerable and hence cannot be neglected. When you talk about short column, direct stress comes into picture. And this theory says that direct stress is completely negligible. Hence, you cannot use this theory for short columns. Next, let's talk about the assumptions made in Euler's theory. Now, while deriving the formula for calculating the critical or the buckling load, Euler has made certain assumptions. The first one is the column should be actually loaded. So as I have shown you before also, this is the column and this is the axis of the column. So this is how the load is supposed to be applied. Now this is a 2D figure. If you want to see a 3D figure, it's something like this. On this surface, you're going to apply your load. So on the axial direction, you're applying your load. Axial means along the axis. The column material is perfectly elastic. Elastic means you apply the load, there will be stress, strain. Once you remove the load, the material will come back to its original shape and size. Homogeneous means there is no void or gap or dirt particles, and the entire column is made very perfectly. And it is completely homogeneous, that is uniform distribution of material is there in all the directions. Now there is something called as isotropic. Isotropic means in every direction, x, y and z, that's the three directions that you study. In all these three directions, the material property will remain same. The properties are E, K, mu and G. E stands for Young's modulus or modulus of elasticity. K stands for bulk modulus. mu stands for Poisson's ratio, and G stands for shear modulus, or it is called as modulus of rigidity. Now, when we talk about these three properties for a column material, it obviously means that the column material is going to follow or obey the Hooke's law. The column should be perfectly straight and uniform in cross-section throughout its length. That is, your entire column is going to be having a cross-section, that is B by D. As I have shown you, this B by D at any section is going to have same number. There will be no change in this value of B and D, which means your column will not be something like this, a tapered form. It has to be completely erect, straight, and the dimensions will be same in every cross-section. Length of the column is very large as compared to its cross-section dimensions. I have told you L will be quite greater than B, and it will be quite greater than your depth D. The column is long, that is, direct stress is insignificant compared to bending stresses. So we are going to talk only about bending or buckling that is happening in the column, which is of long type. According to Euler's theory, there is no direct stress because there is no short column that we are talking about. Plane cross-section of the column remain plane and normal to the center line during the buckling. If you look at the column, I have drawn it this way, and when I show the cross section, okay, it will be something like this. Now, when this buckles, the cross section is still going to remain the same. When it bends, it will be something like this. So, the cross section has not changed. The plane cross section of the column, that is this cross section, remain plane, that is, it was initially of this shape, and it will also remain like this even after bending, and normal to the center line. You can see initially the column has cross sections which are normal, that is perpendicular. This is your cross section and this is your center line. So this cross section is perpendicular, and even after bending, these cross sections are perpendicular to the center line of the column. The self-weight of the column is neglected. As compared to the entire building or any other structure wherein you have columns, the self-weight or the weight of a single column is actually very less. So we say that the self-weight of the column is quite negligible as compared to the entire structure whose part it has become. Next, we'll talk about the types of end conditions of column. Now, this is required because we want to know what is this effective length or the length over which your load is showing the effect. So, for that, there are four types of end conditions which are studied. The first one is one end is fixed and the other end is free. You can see here at this end, I will say that it was fixed, which I have now replaced by this reaction P, and this end is free. So on the free end, you are applying load P on the column. Now when you apply load, this is your column initially, it has now bent in this form because it has buckled as we are discussing. Now the effective length or the length over which your load is showing the effect is 2L. Now it is so because your column was initially straight, this end is free. So when this end is free and the load is applied, there is no resistance from this end. So this column is free to buckle. That is why this LE in theory is found to be twice this L. Now L is the actual length of the column. So we can say that the effective length is 2 times the actual length. Now one more thing that I would like to add here is your column can either buckle like this or it can buckle in the outward fashion. Like suppose it was your initial column, this can buckle in this fashion, in this way, or it can buckle like this, as I am showing you. This is called as concavity and this is called as convexity. So when your beam is showing concavity, this is generally considered as a positive bending moment, and convexity is considered as negative bending moment as per sign conventions. Now this is a sign convention. If you want, you can assume concavity as negative, but in that case, please consider convexity as positive. So your column can bend in either one of the two fashions. if it is free, it can either bend like this, like this is a straight column. This can either bend outwards because of the load, or it can bend inwards like this because of the load applied. Next is both ends pinned. Pinned means a joint like your hinge joint. So this pin is also called as hinged, and hinge is something that everyone has seen. You can just go to any door of your house or in your office. You can see that the door which is attached to the wall is with the help of a hinge joint. So hinge is also called as a pin joint. It's like a pin. The effect is the same. So here, if both the ends are pinned, there will be reaction from this end, and the load you are applying is from the top end. So when this end is pinned, unlike free end, it cannot move. It will be stationary at that point. You can apply the load. The column which was straight will buckle, and when it buckles, this effective length is equal to the actual length of the column. So this is the length over which you are going to see the effect of the column. It can be more or it can be equal. And in these two cases which are upcoming, it can also be lesser than the actual length. So let's go to the third one. One end fixed and one end is pinned. So here I am assuming a fixed end. When I remove the fixed in FBD, we generally show it with a reaction force. And on the pinned end, say I am applying load P. In this case, you will see that the effective length is 0.7 times the actual length. Now this is also written sometimes as L by root 2. Now why is it so? Because if you observe here at the fixed end, obviously there will be some reaction, first of all. And secondly, at the pin end, you can see that this point is not free to move. So here also there is some amount of resistance, but this will at least try to bend, because this pin, this will at least give the free flow to move. But here, because of the resistance, this much length is not to be considered. Only this much length you are going to consider as your effective length. Next, we will go for both ends fixed. When you have both ends fixed, obviously the reaction is to be shown here, and this is the point where your load is applied. The resistance to the load applied, or the change in your dimensions or the buckling, will be lesser. So this much and this much length from top and bottom will be neglected, and this is the only portion in between where you can see the effect. And here your effective length is half the actual length. So these are the four types of end conditions which are possible for a column. Next, we will talk about the relation between this LE and L, and we will also see a formula which was given by Euler. Euler has given a formula for buckling or crippling or critical load. That is what I've written here. E stands for Euler and P is the buckling or crippling or critical load. The formula is pi square EI upon LE square. E stands for Young's modulus, I stands for moment of inertia, LE stands for effective length. So we are going to just show the relation between the LE and L and what could be the change in this formula. So we are talking about the first condition, that is both ends hinged. Here I have drawn a column. These two ends are hinged. So here I am applying a load from the top end, and from the bottom end what you obtain reaction from the hinged part. So this is the buckling that you are going to see. LE is equal to L as we just discussed. Now this is the relation that I am going to fill up over here. Now I am going to write crippling load in terms of effective length. This is the formula that I am going to write. PE is equal to pi square EI upon LE square. And when I want to write in terms of actual length, I am going to substitute LE as L. So PE will now be pi square EI upon L square. Next, let's talk about one end is fixed and the other end is free. So this is my column. One end is fixed, which will show a reaction P if I remove the fixed end. This end is free and here there is a load P. So let me say that the column is going to buckle in this fashion. This point is B, this is A. When this load is applied, it will move to another point B dash. So here the effective length is 2 times the actual length. The formula in terms of effective length is pi square EI upon LE square. When I substitute LE as 2L, my PE will be pi square EI upon 4L square. Next, let's talk about both ends fixed. So this is my column. Both ends are fixed. At this end, I'm going to apply the load P, and this end will show the reaction P. So when it is fixed, obviously there will be some amount of resistance which these ends are going to show to the buckling. So your bending will be something like this, and this will be my effective length LE. For this LE, the relation is LE is L by 2. We know this formula already. When I substitute LE is L by 2, PE will now be pi square EI upon L by 2 the whole square. This will be 4 pi square EI upon L square. And the fourth one is a column which has one end fixed and the other end is hinged. So here when I apply load P, since it's a hinge, I will show with a sign like this. When this is hinged and this is fixed, this will also show some kind of free buckling from here and some resistance from this end. For this LE that I have over here, LE will be L by root 2. This is my formula in which I'll substitute LE as L by root 2. So PE is now pi square EI upon L by root 2 the whole square. When I solve this, I'll get 2 pi square EI upon L square. I would want to add one more thing here just for your visualization, that why would some amount of effective length be considered when you can consider the entire length of the column. Now, as we have discussed, say these are the 4 columns for a particular floor and this is the beam which is connecting over here. So if you observe your house in which maybe you're sitting right now or in some classroom or some office, you can see that this is one floor and this column at the top end will have some amount which is covered by the beam, and below also some amount of the column will be dug inside your floor. These are the two ends wherein you get some load and also some amount of support from the floor below and some load from here above on it. So this is the portion on which you can say that your load is being applied. So this is actually the length in between on which your load is applied. It is not applied on this entire length of the column which is built. And this height of the column which you generally have for your houses is approximately 9 feet to 12 feet depending on what height do you want for your room. And also the height of the column will depend on the total height of the structure. Suppose if you have longer structures, then you would have longer columns and they are more dug inside. At the foundation level also they are dug inside, and at these ends also you will find them more, the height is going to be lesser for the floors or the residential areas or the offices, and you are going to find more area which is dug inside to give it more support so that the columns do not buckle. And it is not about these 4 only. There will be many such columns in the entire structure that you see, and they are all connected through the beams. So they are actually being supported, and also the buckling is going to be resisted because of the composite structure as we have discussed. So with this we end the first introductory session of columns and struts, and what is Euler's theory about long columns, what are the formulas that you are going to use for calculation of critical load for long column and understand its stability such that the column is stable. With this, I end the session. I hope you have understood the lecture. If you have any doubts, please write to me in the comment section. In the next session, we will discuss about the numericals on this topic. See you in the next session. Thank you.